All right, ladies and gentlemen, we're going to be learning about the consensus layer in Ethereum, and our speaker is Mr. Nishant Das. Let's give our speaker a warm welcome. All right, the stage is yours, Nishant. Take it away. Thank you.
Right. Hello, everyone. Today I'll be talking about what we can expect from the consensus layer in the next hard fork. So some background, I've been in Ethereum core dev for many years. So I've been working on the Beacon chain since, I guess, 2018, the merge, and now 4844. So I hope by the end of the presentation, you guys will have an idea of what to expect on the consensus layer and also what rollups can expect going forward. So this is a small history of hard forks in the consensus layer. So in December 2020, we had phase 0, which is the Beacon chain genesis. So that is when the deposit contract was deployed. You had all the validator deposits go in, and the Beacon chain finally launched. In October 2021, you had Altair, which was the next hard fork. So this actually brought in light client support for Ethereum. So what this means is that you had a new construction on chain called sync committees. The sync committees allowed a subset of validators to attest to a particular beacon block root, and using that, you can build light client proofs. So light client proofs can be used by many applications. Some would be, cross-chain bridges, or people trying to build trustless staking pools. September 2022 was the big one, which was Bellatrix, or better known as the merge by everyone else. The merge was in progress for nearly 1.5 years, I think. We were testing it for the last 7 months of it till launch on 2022. And the last hard fork that we had was on April 2023 called Capella. So Capella was a hard fork that enabled withdrawals and allowed validators to actually access their funds on the execution layer. So today I'm going to be going through all the EIPs that are going into the NEB. So I'll just go through them. So EIP 4788 is Beacon block root in the EVM. EIP 7044 is perpetually valid signed voluntary exits. EIP 7045 is increasing the max attestation inclusion slot. And EIP 7514 is adding the max epoch churn limit. And finally, for the start of the show, EIP 4844, which introduces shard blob transactions onto Ethereum mainnet. So starting with EIP 4788, so what this does is that this allows the beacon block root to be accessible by in the EVM. So any contracts on the execution layer can actually access this value. So what this is basically commits to the hash tree root of the beacon chain, and you can use a corresponding execution payload header to know what was the past beacon block root. So what is the main motivation is so that applications have access to consensus layer state. So if you're an application and you're building a staking pool, you would need to know the beacon chain header, beacon chain root, so that you can actually derive stuff like validator balances, validator status updates, and also if you're building a cross-chain bridge, having knowledge of what actually is the finalization checkpoint is very important, because using that you can choose to mint, burn, or redeem funds on either side of the chain. So yeah, what I described. So yeah, moving on to the next one is EIP 7044. So perpetually signed validator exits. So this allows a validator exit to be perpetually valid from Capella onwards. Currently, validator exits are only valid for 2 hard forks. So if you're a validator and you want to exit participating from the chain, you can't just stop attesting. You basically would have to sign a voluntary exit in order to exit from the chain. So the main reason that we are trying to actually introduce this EIP is so that it improves the UX of actually creating a voluntary exit. So right now, staking pools have separation of hotkeys and withdrawal keys. So what could happen is that if you have two hard forks on the line, and the individual that actually possesses the hotkey, they can actually grief the individual possessing the withdrawal key by not signing a new voluntary exit. So you could have funds stuck perpetually in the consensus layer. So to prevent this UX degradation, we allow perpetually signed voluntary exits to be valid for all future forks. So yeah, like I mentioned earlier, you have staking operations where one party holds the withdrawal key, the other holds the hotkey. So you'll only now need to generate signed voluntary exits once. And yeah, okay. We can move on. Okay. So this is the next EIP 7045. So what this does is that this increases the max attestation inclusion slot. So right now, if you're a validator and you produce an attestation on chain, you basically can only have your attestation included in one epoch or 32 slots. So while this was fine when the chain had 16,000 validators, currently right now on mainnet, we are running close to 900,000. So there is a lot of activity on mainnet. And if your attestation is slightly late, there's a good chance it'll be completely missed on chain. So if you basically can extend this, what happens is that you can have late attesters have their attestation included on chain. So instead of being penalized, you get a slight reward. And one main reason that we're actually adding this is that for LMD Ghost, which is a fork choice protocol that Ethereum uses, having a rolling window of 2 epochs for attestation inclusion, it is pretty important in order to generate a security proofs for it. Also, consensus researchers have been working on a confirmation rule for the beacon chain. So what this means is that instead of waiting for a finalized checkpoint to determine whether you can regard this state as completely finalized, you can use a confirmation rule which tells you that in 4 slots, under assumptions of on a certain amount of honest stake or network synchrony, that the chain will not be reorged. So for that, we do need increased max attestation inclusion slot. So yeah, like I mentioned earlier, if you're missing a later attestations, now you have a larger window for it to be included. So the average validator would have a higher profitability because with these missing attestations included, you would have a high reward. And yeah, this is EIP 7514. So this adds a max epoch churn limit. So what is a churn limit? So in every epoch, there's a certain amount of limit that a validator, number of validators that can be active on the beacon chain. So this is dynamically computed by the number of active validators in the state. So as a validator registry grows bigger, from 16,000 to 800,000, the amount of validators can be activated each epoch also grows proportionally. However, having this number too high puts stress on consensus layer clients. So to prevent that, we have proposed this EIP to cap this value to 8. So by having 8, there's a linear increase in the number of active validators on chain. Yeah, so for the ecosystem, what this means is that you would have to wait longer if you have put your deposit in for your validator to be activated. And finally, moving on to star of the show, which is the big EIP, EIP 4844. So EIP 4844 introduces a concept of shard blob transactions on Ethereum mainnet. So this is a completely new transaction type. It is not a standard transaction, so it will not be executed in the EVM. Instead, anyone who wants to propose a blob transaction would just have to sign arbitrary data and submit it to the execution client. So there would be a separate mempool for blob transactions due to the fact that they're much larger than regular transactions. So on Ethereum mainnet, a single blob would be 128 kilobytes, which is much, much higher than what is a normal Ethereum transfer transaction. So the main benefit of having shard blob transactions is that this provides cheap space for rollups to post the data in. So why have we decided to use blob transactions? So very simply, we need blob transactions in order to have it ready for full dank sharding. So rollups, before they ossify, they will need to upgrade once to, instead of using call data, you use blob data. So it is better to set the stage earlier rather than later on in a few years down the line when it would be much more difficult for a rollup to change the internal mechanics to use blob data. So another advantage of having it now is that all execution layer logic required for full data sharding will already be in Ethereum mainnet in 4844. Also, another big reason is that it allows a separate fee market for blobs. So currently, rollups, when they post data on chain, they post in Ethereum call data. This actually competes with normal transactions, which are trying to call contracts. If you want to do a swap transaction and stuff, you're actually competing with all these big rollups who are actually trying to post the data on chain. So by having a separate fee market, you can basically have a market solely focused on posting blob data on chain. So this is a summary of block space versus blob space. So in both cases, blocks are also seen by all nodes. Blobs are also seen by all nodes. Theoretical limit, the highest, the limit of an Ethereum block is actually 1 megabyte, while the highest limit of the number of blobs in a block, which would be 6 right now, would be about 750 kilobytes. The big difference with 4844 is that blobs, instead of being stored in the execution client, will now be stored in the consensus client. Call data can be accessed via the EVM, while blob data cannot be. One big difference is that block data is stored forever, while blob data has a window of 18 days. So for that reason, call data is expensive, while blob data is much cheaper. So yeah, you guys can take a look at this diagram. So this is from Proto Lambda. So he works at Optimism now, but this can tell you how exactly the roll-up centric roadmap will actually work after 4844. So you would have all these separate roll-ups. They'll be posting blobs, and these blobs would actually be in individual blocks rather than as part of normal transactions. So how do we attach blob into blocks? So we use what we call KZG commitments, which is a polynomial commitment scheme. So why do we use polynomial commitments rather than something that is very standard like SHA-256? The reason is that an arbitrary blob can be thought as a vector of 496 field elements. So what this means is that any arbitrary blob can be represented as a polynomial. So having it represented as a polynomial actually enables recovery using certain encoding schemes like Reed-Solomon. So this is a necessity for full dank sharding. For data availability sampling, you will not have all the field elements available, and you would need to be able to recover it. For SHA-256, since it's a non-arithmetic commitment, you cannot use it to recover these missing data chunks. So one interesting thing in the consensus layer is that blobs are decoupled from blocks. So when a proposer creates a block, it'll broadcast it to the network. And this block will not actually contain blobs. It'll instead contain the KZG commitment of these blobs. So blobs and their resultant KZG proofs are kept, in a separate construction or structure, you could call it, as a blob sidecar. So the blob sidecar contains three things: the blob data, the KZG commitment, and the KZG proof. So initially, the sidecar just consisted of the KZG commitment and the blob, but because verification of KZG commitments on a normal node take 40 milliseconds, we needed to add a KZG proof, which brings it down to 3.5 milliseconds. So also one restriction of having these decoupled blocks and blobs is that blocks can only be processed when the respective blobs have also been processed by the node. So the block will have to wait for the node to see all the blobs before it can continue processing it. So one important question you guys might have is, why have we decided to decouple blobs from blocks? So we probably can't see it from this PR, but this is the title of the PR is called "Free the Blobs." So the reason we want to free the blobs is because blobs are very large, and a normal beacon block with 6 blobs would actually take about 1 megabyte in size. So this would actually saturate bandwidth in the network and have negative effects on latency and bandwidth consumption for all nodes. So when you actually have blobs separated out into different subnets, what happens is that you have separate meshes that these blobs can be gossiped in. So what happens is that you could have high bandwidth nodes in a certain mesh propagating these blobs, and basically the blobs would go along the path of least resistance. Whereas if these blobs were coupled to blocks, basically almost every node would have to gossip them. And certain nodes on the network are bandwidth constrained. So if you have a 1 megabyte blob being translated, and you have someone with a 10 megabit up and down line, it'll take literally 1 second to just download the block. So to prevent this sort of congestion on the network, we've decided to decouple them. So having a smaller message size in the case of decoupled blobs actually allows for bandwidth reduction techniques. So this is implemented in the gossip layer. So with bandwidth reduction techniques, they're much more effective if the message size is small rather than larger. So yeah, like I mentioned earlier, bandwidth can be used much more efficiently. You have independent meshes on all these blobs can be transferred on. So yeah, this is a nice chart from Anton from TXRX. So this is a simulation that was done on decoupled and coupled blobs. So on the left, you can actually see the latency is much slower for decoupled versus coupled. There is a larger spike, but that is because the higher traffic nodes which have a large amount of bandwidth, this is through which all the blobs are being propagated on. So yeah, this is a chart, so you can see on how it works on varying bandwidth capacities of different peers. So now we move on to what these shard blob transactions mean for the ecosystem. So L2s right now are bottlenecked on posting data on chain. For almost all L2s, the main costs that they pass on to users is actually the cost of data that they post on the Ethereum mainnet. Call data is expensive, it is kept forever, and due to DOS concerns, that is why its price is so expensive. With shard blob transactions, L2s have an alternative route to post data, which is through these blobs. So these blobs are much cheaper. Estimates have put it at about 10 times cheaper than current call data. So for the securities of L2s, especially optimistic rollups, you basically need the data to be available for at least 7 days. Well, currently for 4844, it'll be for 18 days. So this actually allows, in the event there's a invalid state assertion, that you can actually challenge it effectively. So 4844 provides cheap data storage that all L2s can utilize. There might also be non-L2 use cases for 4844. Maybe some NFT project needs a cheap and less permanent place to keep their JPEG metadata or something. So yeah, this is a small chart from a colleague, Terrence. Basically, this is how batch posting will work post 4844. So you would have the L2 batch poster. They post the data batch to the execution client. So the execution client will package it into a blob transaction. Then when it's time to propose, the consensus layer client will take this blob transaction and build a block with it. Using that, you broadcast to the network, and you broadcast it separately to the network. So the blocks will be broadcasted as one set of peers, while the blobs will be broadcasted to another set of peers. And yeah, I think that is all.
Right. Thank you very much, Nishant, for that explanation about blobs. I like the phrase "free the blobs." The only joke for the entire day. All right, let's open up for questions. Anybody got questions about the consensus layer? CC, you got a question? I will pass you the mic. He's just here, second row. You can raise your hand. Yeah, there we go.
Yeah, quick question. Is the data sampling challenge and the data recovery implemented in 4844?
Oh, so no, it isn't. So it is a big to-do. So basically, 4844 is actually setting the stage for data recovery and data availability sampling, but it will not be implemented in 4844. Well, what 4844 does is that it builds like all the requirements for rollups to use a cheaper form of storage. So in the future, when we do have full dank sharding, rollups won't have to change anything. So the execution layer client logic will be unchanged. The only thing that might be changed will be on the consensus layer.
Okay, thank you.
Okay, thank you for the question. Thank you for the answer. Anyone else? Over this side. Oh, I'm so sorry, I didn't see behind me. Can pass. No. Not him. Him. He was pointing to him. Yeah, the guy in the black shirt at the end. Please introduce your name as well as your question. Thank you.
Hey, thanks for the talk, Lib. I got a question regarding 4844. Like, why do you think that it should be a hard fork? Why is it like an EIP? Why isn't it like a sidecar that is an optional add-on? Because it seems like, the history of Ethereum is that you let the protocol layer be as flexible as possible, but this seems like a very application-specific thing for like blob transactions for L2s. Why don't you keep the layer light and have this sidecar, optional sidecar, just like PBS, and then enshrine it in the event that it does become popular?
I mean, if you do the latter, you have issues like Lido popping up. So, but one reason that we want to do it now is that we do understand that Ethereum is being used for rollups a lot more than it was 2 years ago. There's a definite need to have cheap rollup transactions, even though it's a bear market. So at least having this set right now would actually allow rollups to upgrade to using this blob space rather than the cheap call data. I mean cheap, but call data that they use right now. Also, a lot of things that rollups require do need a hard fork, so you can't actually have it optionally. So like they need some EVM opcodes to be implemented so that they can actually determine what is the gas price of blobs and stuff like that. So I don't think it can be optional.
Gotcha, thanks.
Thank you for the question. Anyone else? Raise your hand. You got one? Oh, the two over here. Yeah. Go ahead, and then we'll pass it to the back.
Yeah, regarding 4844 as well, how much of a performance degradation does 4844 has on the consensus clients?
So there was significant bandwidth issues with the old design where blobs and blocks were coupled. So after decoupling it, there might be a slight increase in bandwidth, but due to blobs, being broadcasted on separate meshes, it is a lot less than what it was before. So in terms of block processing times, the only gotcha is that because blobs and blocks are decoupled, all clients will have to wait to see all the blobs before they can process it. So there are certain edge cases where a malicious proposer could just broadcast this block with these KZG commitments, and it will not broadcast the resultant blobs for those. So you could just have the client waiting to see the blobs. But yeah, that is one possible downside, I could say.
Thank you. Sorry, one more question. Regarding 4788, is the contract going to be introduced as a pre-compiled contract, or is someone going to deploy that contract and make it trusted? Yeah.
So from what I understand, it will be a pre-compiled contract. It's still being audited, but yeah, that's what I understand.
Thank you for the question. I can pass to the gentleman at the back. Do Ethereum developers ever laugh when they say, "Can I see your blobs?" It sounds very funny. Okay, please go ahead, sir.
All
Thank
right,
you.
I think you touched a little bit of in your previous answers. So my question is, you mentioned that the block and the blob will be detached and propagated separately, right?
Yeah.
And then and you also mentioned that the block cannot be finalized if you don't receive the blob, right? So does it mean as a consequence we won't be having two epoch finalization?
Oh, no. So that is a separate thing. Basically, if, let's say, a malicious proposer broadcasts the block without the blobs, it will not be inserted into like the client's fork choice. So the fork choice is like, you can think of it like the internal like linear chain or internal chain that the node uses to determine what is the head. So the blob doesn't come in, it's not processed at all. Just that there's a weird case where it waits for the blob in order to be processed. So there's a timeout, I think, that's implemented in all clients. If after X amount of seconds you don't see the blobs, you just drop the block. Yeah.
Thank you. Anyone else want to ask a question about blobs? Oh, yes, in the front. Yes, come. We have one in the front here. If you don't see the blobs, drop the block. Yeah, I'm going to remember that. Write it down on my Instagram.
It's not about blobs. So you've been as like corn dev for a long time, and you probably realize there aren't many corn devs in Southeast Asia. For those who want to be a corn dev in the Ethereum space, do you have any suggestions?
Yeah, so Ethereum has this really cool fellowship program. So a lot of, I think, new people who join core development, they have actually come to the program. So we've actually hired a few people who have participated in the fellowship program, and using that, they're now part of Prism. So, if there's anyone in this room who's actually interested, definitely do check it out. We have a lot of cool projects that, maybe core developers can't focus on, but they have been picked up by, all the fellowship participants, and they've done a great job with it. So, if you're a core dev and this is something that interests you, you can definitely try that.
Great, thanks.
Anyone here interested to be a core dev for Ethereum? Oh, we are. Oh, some. Yeah, join the fellowship program. You have a... He's a fellow, or he's already a fellow. Yeah, it's okay. That's fine. Any last questions before we wrap things up? Anyone else want to ask something? Yes, okay, yep, come. When he asks questions, it sounds like interview. But it's okay. It's okay. Questions are good.
Sorry that it sounds like.
Don't apologize. We still got 5 minutes. Please go ahead. Yeah.
Okay, I wanted to ask what's after Denkun. So on the execution side, there has been talk on EOF and vocal tries. I'm specifically more interested in the vocal try side. If, let's say, vocal tries were to be implemented, what are the changes that the consensus side should take note of? Yeah.
So for vocal tries, I don't think the consensus layer has to do many changes. Probably due to how the vocal tree be bootstrapped, that'd be one concern. But I don't think off the top of my head there's something we have to worry about.
I think there has been talk on including proofs in blocks itself. So I'm not sure if I still remember correctly. Do you have that insights on that? Yeah.
There might have been conversations, but I'm not too sure about that.
Okay, Cool.
Yeah.
Okay, thank you very much. Anyone else? Going once, going twice, 3 times. Let's give our speaker, Mr. Nishant Das, a round of applause.